technician for these. Not
Okay.
here.
So we use it. Hello. Good morning. So we should slowly start. Thank you. So good morning, everyone. Welcome to the third day of the conference. So we are in the equator of the conference, and it can only get better, especially after yesterday's party. I hope you could enjoy. I was enjoying it a lot. Thank you, Ramon. I don't know if Tim is here. It was a great experience. Thank you. So today we are on the first session of Advanced in InSAR Theory. Remember, tomorrow we will have the second one. And we will have very interesting presentations, 5 presentations, and the topic is basically in all of them, these non-closure phases or fading signal. So we are all looking forward to these new advances in this topic. And I remind you, please think on these seed questions or these recommendations on InSAR, because I guess we will have to gather a few of them concerning this particular topic. So I would like to introduce the first speaker. It will be Jacob Matthew Connolly from the University of Leeds. And the title is A Comparative Study of Phase Bias in C-band and L-band InSAR.
Hi, everybody. I'm Jacob. I'm a PhD student here in Leeds. I'd like to present some results on phase bias, comparing C-band and L-band. So I think there's been some talks already on the subject, and there's some more after this. Okay. The phase bias is a sort of nuisance signal that we see in time series InSAR that mostly affects multi-look short-term interferograms. So interferograms where we want to use short temporal baseline to improve coherence, and multi-looking to also improve coherence. And sort of the main way we're sort of diagnosing this problem is by looking at the loop closure. So you're probably mostly familiar with this by now, but you can create a closed loop of phase by 2 or more smaller interferograms and a longer interferogram spanning the same timescale. And if these interferograms are multi-looked, then the loop closure can be non-zero. And these sort of small contributions that we see in these small interferograms can contribute to bias deformation. So this is a figure from InSAR et al. In 2021, and you can see on the panel on the left, it's quite heavily biased, or at least it looks like there's deformation velocity downwards. And this method on the left is using short temporal baselines. The method on the right is a PS processing scheme that's less affected by phase bias. It uses generally longer interferograms. You can see that the majority of the deformation doesn't actually exist in this interferogram. So hopefully that convinces you that phase bias is an interesting problem to study if you're not already convinced. But the main conclusion from the study that it varies by land cover. So sort of pointed towards the idea that variations in vegetation and soil moisture could be causing this, causing some sort of signal that we see inside time series. So that leads us on to motivation for this talk and my study, to try and understand a bit more about the mechanisms that cause phase bias. And if we know that it varies by land cover and the sort of types of vegetation that we see on the ground, then it sort of tells us that there's some mechanic happening. And if we look at different wavelengths, then hopefully we can see something there. So I'm mainly focusing on trying to compare the bias in L-band and C-band. Specifically, I'm looking at phase closure as a way to sort of diagnose the problem. And then ultimately, what can we learn about the underlying physical mechanisms from this data set? So for C-band, generally, they'll be scattered by the top of a canopy and some of the sort of smaller branches at the top. And L-band L-band, it can penetrate a bit further, hitting some of the large branches in the tree trunks themselves. So you get a different sort of scattering depending on the vegetation. So I'll be focusing on how and where the phase misclosure presents itself for L-band, comparing that to C-band. For our study region, we're looking at Milan in northern Italy and its surroundings. So we're mainly dictated by where L-band data was available. So we're using data from ALOS2. As you know, ALOS2 doesn't have complete coverage over the world that's sort of freely available. This is data was gained through a research agreement. We have almost a complete time series for our time period, so September 2020 to 2021. So it's generally 14-day repeat with some larger gaps in there as well. And the other advantage of using this area is that we can take advantage of the C-band interferograms from InSAR. So looking at land cover, you can see that there's a large urban area where Milan is, and you also have a large amount of cropland and grassland across the middle band. And along the rivers, you can see quite high vegetation, or at least tree cover. And so those are the main areas I'm focusing on. So the middle cropland area, the tree cover, and then the urban area towards the north. So we can first construct some C-band closure loops. So I'm using 4 6-day interferograms and a 24-day interferogram. The InSAR processing system uses 5 by 20 multi-looking. And so if we sum the 6-day interferograms and subtract from the 24-day, we get our closure phase. You can already see some correlation with where certain areas of land cover are. So across the middle band where the crops were, you can see generally non-zero. Where the city is, it's generally 0. And we can also sum this for the whole time series. So if we do lots of connected loops across our study period, you can sort of see the phase bias, or just the loop misclosure build up. Comparing it to land cover, you can see where the city is. It's generally fairly flat in the map. So this is down to generally being quite coherent. Across the cropland and grassland, it's fairly non-zero. We can separate that out by land cover a bit further. So if we do the whole time series and do the cumulative mean closure phase for each class across the whole period, and these results are in line with other studies where we find that grassland and cropland are contributing the most to the phase misclosure, with tree cover and then urban being below that. You might notice that urban is still fairly high in comparison. I think this is because there's some of the sort of tree cover vegetation class mixed in with the urban class, particularly in the city area where we have pockets of vegetation that are misclassified when we downsample the land cover map to the interferogram resolution map. So this is something that I need to look into a bit further. But I think in general, it's what we expect. So we can also look at L-band now. So for L-band, I'm using sort of triplet phases, triplet loops. So in this one, it's 2 14-day interferograms and a 28-day interferogram in June, July 2021. You can see, again, it's a similar story. We have a fairly flat closure phase, so close to 0 for where the city is, and then around the city, and then along the river, you can sort of make out more of a red tinge there. So to sort of visualize this a bit better, we can downsample the closure phase a bit more to make it a bit easier to see. You can see where the city is, again, fairly flat. But I think the most important and sort of interesting result is along the river where we have the more dense vegetation. We're getting more non-zero closure phase. So if you remember, this is quite different from C-band where it was mostly across the cropland and grassland, whereas here it's across the sort of heavier vegetation. So we can separate this out a bit further for L-band and C-band. You can see that the tree cover actually comes up on top. And so this is sort of points towards the idea that the phase misclosure might be being caused by volume scattering within the vegetation. So for L-band, you're going to have more volume scattering across sort of larger branches and tree trunks and things like that. Whereas C-band, you'll have more volume scattering for sort of smaller trees, cropland, and sort of lower-lying vegetation. So those are the main results so far in the study. Sort of fairly brief, but I think it's quite interesting conclusions so far. And there's definitely more work to be done. But essentially, as expected, cropland and grassland exhibit the highest cumulative phase closure. Yeah, for C-band, and then for L-band, it seems to be more on the forested areas with the thicker vegetation. So the main conclusion is sort of that the volume scattering might be the main mechanism that's causing this non-closure crown loops. Obviously, going forwards, I think more needs to be done, particularly looking at different vegetation types. So drier or wetter climates and different levels of sort of trees and sort of shrubs and things like that. Just to acknowledge that the LS2 data, as I said, obtained through a research agreement, and say thanks to Milan and Jesse for posting InSAR and sort of discussion on phase bias. I've also got a poster, so if you'd like to discuss my poster, it's on change detection or this work more, I'll be there tomorrow afternoon. Yeah, poster number 50. Thanks.
So it seems we have quite a bit of time for questions, so let's just open it to the audience. I don't think we should start too early with the next one, so we have 5 minutes.
Okay, I just had a question. Why is the closure phase always seem to be have the same sign? And what's the origin of that?
Yeah, it's a good question. I think so I think there's always sort of bias towards your shorter interferograms. So because you have you're creating loops of your short interferograms and you're minusing your longer interferograms, then that sort of phase inconsistency is usually always one way. In terms of the actual physical mechanisms, I'm not entirely sure why that would be the case.
I was wondering, for a fair comparison between the C-band and L-band, if you would have used 12 days for C-band as well, because you use 6 days. So these things are very time sensitive.
Yeah.
That's one comment. And then, yeah, obviously the results are not intuitive. I would have expected more closure for the L-band, but yeah, maybe it's because of the time. And to answer your question, Charlie, I think you have to wait for UGS presentation. It's not always the same sign, actually. Yeah, it's not the same sign.
Thank you. I just saw your graphs roughly, and when I recalculate the radians to centimeters, I get roughly similar values. Am I right?
Sorry, can you repeat the question?
I remember that in your graphs it was 0.6 radians for L band and 3.5 radians for C band. Just roughly recalculating, it's like 18 centimeters, both of them.
Yeah.
So it's similar in radians, similar in centimeters,
Okay, I see. Yeah.
but heavily different in radians.
So yeah, are you saying it's similar sort of distance
Yeah.
for both C band and L band?
So if we measure it in centimeters, we can quantify it more general.
Yeah.
Thank you.
In your study, you relate the cumulative closure phase to the land use. For the understanding, I would suggest that you also relate it directly to the coherence. In addition, I mean, it's not, you should do it for the land use, but also to look at how it relates to the coherence. Also, with the different frequencies, that may also give some indications how you can model it or understand it, I think.
Okay. Thanks.
Hi. How sensitive is the phase closure bias to the level of multi-looking you do?
So it can increase with more multi-looking. So I think it varies on the sort of type of terrain you have, particularly if it's very vegetated, then you'll probably have more of a bias, the more multi-looking you have. I think the main sort of factor is sort of the length of the interferograms. So as I mentioned, it's quite sort of time sensitive. So generally, the shorter the interferogram, that has more of an effect for sort of the bias you can see.
Okay, just could you help me to go back to the slide 19? So just one slide back here. Okay, so I saw that you observed the phase. So the closure phase is not zero even in the urban class. So what is the reason behind for this one? Because basically that's with the closure phase we have problem with the water content, something like volumetric target. So in the urban cluster, basically why we don't have it should be very close to zero, but why I saw it's not non-zero now, and what exactly the reason behind the physics behind what is the cause?
So I believe it's the urban class obviously doesn't cover completely urban areas. In between, there'll be sort of vegetation within that class, and obviously variations in sort of weather and sort of moisture levels within that will cause different levels of variation in vegetation across our time. So I think there's still obviously a bias within that class, but in general, it's less because of the sort of more stable scatterers versus vegetation.
It means when you calculate, maybe there is some vegetation inside that window, even in the urban, so maybe that's missed classification.
Yeah.
Okay, thank you.
Yeah, so I think the sort of main issue with that is it's quite a high resolution Lancaster map, but when I downsample it to resolution of interferograms, some of those classes get mixed up, so it's not completely accurate.
Okay, I think we have to move on. The next speaker is Yasser Maksudi from University of Leeds, and the title, which I think sounds like a good seed question, towards universally applicable phase bias correction for short-term multi-looked interferograms, challenges and progress. Please.
All right, good morning, everyone. So in this presentation, I'm going to give you an update over our recently funded InSAR project, which aims at developing a universally applicable phase bias correction for short-term multi-loop interferograms. So let's make the introduction brief. So it has been shown in several studies that the velocity, which is estimated by the multi-looped short-term interferograms, reveals a systematic signal, which is also called as the fading signal, which actually cannot be explained by any of genuine deformation or any atmospheric or topographic signal. And we previously developed an empirical mitigation strategy for the phase bias correction. And as a summary of the method, we use the observations are basically the loop closures, as you see on the left side of these equations, delta phi. And the unknown terms are the bias terms, which are shown by these delta values in these equations. So this is basically an undetermined system of equations. So in order to solve this rank efficient system, basically what we introduce in as an assumption that the bias is an interferogram is linearly related to the sum of the biases in the shorter interferograms, which span the same time. So what this assumption means, basically, it means that although the bias is changing in time, then the ratio of the 12-day bias and the 6-day bias, and also the 18-day bias and the 6-day bias remains constant. And so this was the main assumption that we had here. So this ended up to this new set of equations, as you can see at the bottom. And then this, in this equation, A1 and A2 are the calibration factors, as I mentioned, which can be estimated using the method that I fully described in the paper, in the published paper below. And this can be easily solved by any least square inversion, and then after estimating the delta phi, the interferograms can be corrected accordingly. So we compared the method with in a highly vegetated region in Turkey, and as you can see in the left scatter plot, we have the original velocities in the x-axis and the phase linking approach in the y-axis, and it is quite clear that the velocities are biased in the first plot. But in the right scatter plot, as you see, we have our corrected estimated velocity versus the phase linking velocities, and again the distribution shows that we had a better match between these two after correcting the interferograms. So one of the main benefits of the algorithm is that our mitigation strategy is immune to long-term coherence loss, because it is basically only dependent on the short-term interferograms in the system of equation for estimating the correction terms. And also, unlike the phase linking approaches, as our proposed method only requires, as I said, the short-term interferograms. It doesn't rely on the availability of the long-term interferograms and long-term coherence for the phase linking approaches. But anyway, the universality of the method needs to be further investigated. So today, basically, as a part of our InSAR project, we recently finished the phase bias characterization stage. And so what I'm going to explain today is actually to use one of the main symptoms of the phase bias, which is the closure phase, non-closure phase. So what we are going to show you is the loop closure time series in different regions, the loop closures in ascending and descending, the effect of filtering and multi-looking, the land cover dependency of the loop closure, and also the polarization dependency, and finally, just making some correlation with some environmental proxies. So these are the selected frames that we use in this study. We selected one ascending and descending frame in Turkey. In Turkey, the average rainfall is about 300 millimeter per year. It is vegetated. In some areas, we have forest. And also, we have one frame in Azores Island, which is densely vegetated with a very dense forest. The average rainfall is about 900 millimeter per year. And also another frame in Italy, which covers the Campi Flegrei volcano. The average rainfall is about 500 millimeter per year. It is also, have a pretty dense vegetation, but not as dense as Azores. And finally, two frames in Tian Shan, which have an average rainfall of 250. So in Turkey, Campi Flegrei, Azores, the acquisitions are 6 days, and in Tian Shan, it is 12 days. So in the first experiment, I'm going to show you how the time series of the loop closures look like. So the x-axis is time, the y-axis are the mean values of the loop closure. So basically what you can see here, this is in Turkey. And so each point in this plot shows the mean value of the loop closures in a single loop, which is obtained using an 18-day interferogram and the corresponding 6-day interferograms. So you can see how they change in time. And so if you look at the peak values in this plot, you can see that the peak values always happen sometimes in early June. So this is the peak value of the loop closures that we have got with the value of around minus 0.2 radian. And so we did the same for 3 other regions. The top left is in Italy. And again, you can see the same seasonal pattern that we have. But this time, the location of the peak value is a bit different compared to Turkey. And this time, we have the peak values in May, which basically is due to the different precipitations, different vegetation growth that we have in Italy compared to Turkey. In Tian Shan, the story was a bit different. And the peak value was about minus 0.1 radian, which is much more smaller comparing to Turkey and Italy. And also the peak values occurred sometimes in March. So every year, this is repeated every year, the same pattern. And finally, in Azores, we had the largest values of the loop closures with a peak value of about minus 0.4 radian. And it is more complex comparing to the others. We cannot derive a seasonal pattern. We cannot see a seasonal pattern in Azores. And this, I mean, in this region, we have the vegetation throughout the year. And so it is not, I mean, we do not, because of that, we cannot see such a seasonal pattern here in Azores. And so, I mean, this was not only about the 18 and 6-day interferogram. You can see the same pattern in the other loop closures as well. This is, for example, the 12 and 6-day closure phase, exactly the same pattern, the same location for the peak of the loop closures, but basically different values, which is expected. And if you want to see the cumulative sum of these loop closures in different regions, you will come up to this plot. The bottom plot is the one that we obtained from Azores, and the cumulative rate shows that it has a very fast rate of change in Azores. And then we have the plot for Italy, and the next plots are for Turkey, and finally the top one is for Tian Shan, and that's where we have the least concern about the phase bias. So next, I'm going to compare the ascending and descending. So for this purpose, I selected one ascending and descending frame in Turkey, and you can plot. I plotted them in the first one, as you see in the top. And in Turkey, actually, the ascending and descending were acquired in the same day. There was not any difference in that, but the timing were basically different. And the blue one are the mean value of the loop closure for ascending, and the orange one are for descending. And so this is for Turkey. For the bottom plot is for Tian Shan. This is 12-day acquisition, and so again, you can see that we can see a good match between the descending and ascending, and this is also quite clear from the scatter plots on the right. And so in this way, we wanted to see how the phase bias is dependent to the look direction. And so again, if we look at the cumulative phases, especially for the ascending and descending ones, the top ones are for Tian Shan. As you see in the cumulative plots, they are completely matched with each other. They are overlapping each other, and pretty much the same trend in Turkey, the ascending and descending frames, which are shown by blue and orange. So this suggests that the phase bias is a lesser concern in the estimation of the east-west velocities, but takes on greater importance when you are estimating the vertical velocities. Then the effect of filtering. So it is a very common practice to reduce the phase noise using filtering. And in Comet LIXAR system, we generate both the filtered and unfiltered interferograms, as you can see in the bottom. The unfiltered interferograms are simply multi-looped by factors of 4 and 20, but no filtering were applied, whereas in filtered interferograms, we have an additional Goldstein filter applied over the interferogram. And it is important to know how much this filtering will increase the closure rule. So this plot shows, again, the same time series of loop closures. The blue one are the unfiltered interferograms in time. And so the Goldstein filters are by orange. And we also apply the boxcar windows of size 10 and 20, which are shown by green and red in this plot. And as you can see, there is a significant increase after applying any type of filtering to the already multi-looped data that we have here. And we did the same in Turkey and Tien Shan, and the same pattern, but the main difference is that the values of increase in the loop closures is smaller in Turkey, and particularly in Tien Shan. And this basically is due to because they are less vegetated, the precipitation is smaller, so the effect of filtering is also smaller. So we cannot say generally that the filtering has the same effect everywhere. And also maybe in this scatter plot you can see the effect of filtering in a more clear way. So in Italy, Turkey, and Tien Shan, and also I plotted the slope of the regression line, as you see here, and the highest value was for Italy, and then the lowest slope of the regression belongs to Tien Shan. Next, I wanted to show the land cover dependency of the loop closure time series. But before I go to the loop closure time series, it is good to have a look at the cumulative loop closures in Tien Shan and Italy, which are plotted on the left panels, and compare them with the cumulative loop closures, which are to compare them with the land covers in the right. And so the land covers are derived from the Copernicus Global Land Cover Service. And so here I plotted the croplands with yellow in the right side. So, and if you compare the cumulative loop closures, which are shown in the red in the left panel, you can see that there is a correlation between the croplands and the loop closures, both in Tien Shan and also in Italy. The same pattern. In Italy, you can see the concentration of the croplands are in the coastal regions. We can see the same pattern on the cumulative loop closures. And in this plot, you can see the mean value of loop closures in different land covers. And so basically, as a general result, the croplands has the highest. The croplands and shrubs had the highest values of the loop closures. And the urban regions, which are plotted in purple in this plot, it's barely visible, but they has the lowest values of the loop closures. And also it is interesting to see that how the forest regions and the croplands regions are comparing with each other. And on the right plot, you can see that you can see the forest on the x-axis and the cropland on the y-axis. And as it is clear from the scatter plot, both the forest and the croplands has a seasonal pattern in the loop closures, but there is a systematic difference, a systematic offset between the forest and, let's say, land covers. The croplands. And if we focus on the different forest species, different forest classes in Italy, we'll come up to this plot. And so again, as you can see here, in the highest values of the loop closures belong to the open forest, and the lowest values belong to the closed forest. And so the open forest has, less canopy cover, and the signal penetration is higher. So that's ended up to larger values of the loop closures in the open forest. And so pretty much the same results in Azores, although in Azores the differences are more pronounced comparing to what we saw in Turkey, especially when we compare different forest classes. You can see they are quite different from each other in Azores. And again, the open forest has the largest, the closed forest has the smallest. And so basically, although this kind of loop closures will result to some biases in the velocities, but on the other hand, this could be used as a kind of loop closure signatures for discriminating different maybe forest species or different, or in general land cover classification, which it needs further investigation, by the way. And next, the loop closure time series in different polarization. And so in the right panels, you can see a single loop closure in VV and VH. The first one is loop closure in VV and the same loop, which is plotted in VH. And the histogram shows that the values of the loop closures is significantly increased in the VH comparing to VV. In VH, we have different scattering mechanisms comparing to VV, and also the coherence is basically lower in VH comparing to VV. And if I want to plot this in the whole time series, then I will come up to this plot. So in this plot, I'm comparing the VV and VH in a frame in Turkey. The orange one is the VH mean loop closure, and the blue one are the VV ones. And so there is a slight difference in each of the mean values of, and I mean, this maybe experiment could be repeated in different land covers to see how they change in different land covers. And also the scatter plots show the same thing, as a slightly increase in the loop closures in the VH. And also finally, I wanted to show you how the loop closure time series can be compared with some vegetation indices. And because as we saw earlier, there seems to be a good correlation with the vegetation indices as well as the vegetation growth as well as the loop closures. So I selected the NDVI, which is a widely used metric for quantifying the health and density of vegetation, and I obtained from the Copernicus Global Land Service. It is every 10-day data from the spot vegetation collection. I plotted them in Turkey and Italy. So we can see a match in the increase and decrease of the NDVI and the loop closures, although in some cases we see a lag between the peak of the NDVI versus the, yeah, sure, thanks. And the peak value of the NDVI and the mean loop closures, which is basically because of the NDVI is a measure of the tree, the vegetation greenness rather than the vegetation growth. So maybe selecting some other proxies for the vegetation we can find a better match with the loop closures. And we have the same pattern in the soil water index, as I showed by the SWI. And again, I obtained them from the Global Land Service of Copernicus, and they are obtained from the scatterometer measurements. And again, in some cases, there are some differences, which is basically, these are the mean values. And the soil water index maybe is not reliable, it's not meaningful when we have a dense cover of vegetation. So maybe in the next part, I need to check this in different land covers. So as some take-home messages here, the loop closure time series has a seasonal trend, as you see, and it is different in different regions. And also in ascending and descending, there was not a significant change of loop closures in ascending and descending. In the effect of filtering or any other box called filtering can significantly increase the closure phases. And I showed the land cover dependency and also the polarization dependency. And I compared with some environmental proxies. So in the last slide, just for our future directions in this project, so we just finished the phase-wise characterization, which you can see here, but the next step is algorithm consolidation, which we need to check the universality of the algorithm and then implement the processor and do the scientific validation using the phase linking approaches. And finally, we will do a larger scale demonstration by using the Comet LIXAR system before and after running the correction. So the final output would be an open source package which take any stack of interferograms and provide the correction. So that concludes my presentation, and I'm happy to take any suggestions, questions, or comments. Thank you.
Thank you. There is room for one short question.
Hi, Hi, thank you for the presentation, very interesting. I was wondering how does this look disclosure is influenced with the multi-looking? So if you have different multi-lookings, like 30 meters or 100 meters of pixel resolution.
That's a good question. Actually, what we compared is because the data that we had were already multi-looked by factors of 20 and 4. So what we did, we applied some boxcar filtering, which pretty much the same as multi-looking, and you saw that they significantly increase the loop closures in time, but with different values in different regions. But it is a good practice to check this with maybe the full resolution originally, before any multi-looking, and then check these with different multi-looking factors.
Thank you, Yasser. So I introduce the next speaker. It's Elizabeth Wick from the Stanford University. And we continue now with the topic as a proxy in this case for soil moisture. So the title is InSAR Closure Phase Time Series for Soil Moisture Measurement.
Hello, I'm Elizabeth Wigg, a PhD student at Stanford, and today I'll be talking about a way to measure soil moisture from InSAR Closure Phase Time Series. Now, the reason we might be interested in soil moisture data from InSAR is that SAR can deliver measurements at field scale, enabling higher resolution than passive radiometric measurements and more complete coverage than in situ measurements. So the goal of this presentation is to show one way that we can relate closure phase time series to soil moisture. We'll show how we do this with a simple model and with some real data. We use a model for the dielectric constant of soil at different moisture levels based on Solar and Ulaby. Changing soil moisture, such as the sequence shown on the right of rapid rainfall events and slow drying, changes the real and imaginary parts of the dielectric constant. We'll show that these changes can affect the closure phase. We start by defining closure phase as the phase that comes from a circular combination of 3 interferograms taken from 3 InSAR image acquisitions. Combining the phases from interferograms 1, 2, 2, 3, and 3, 1 produces a closure phase. In the case of ground deformation, shown on the left, the closure phase is always 0 as all phase components are canceled out in the loop. So the arrows going down sum to the same length as the arrow going up. This is also the case for any individual pixel in an interferogram that has not been multi-looked. Like deformation, atmospheric noise and other single-layer phenomena do not produce a closure phase. However, when multiple layers of scatterers are changing independently, the signals from the layers interfere with one another, and the interference signal varies in time and from pixel to pixel within the multi-look window. In the multi-looked image, the closure phase arises from scattering interaction of multiple layers, such as changing soil moisture below the ground surface and changing vegetation canopy above it. Therefore, non-zero closure phase arises from multi-looked, multi-layer materials that are changing over time. We create a scattering model to demonstrate how this can happen. We start with a simple 2-layer model. Here the layers represent the ground surface and subsurface for soil moisture. We derive the received echo, normalizing the phase and path delay to the return from the ground surface. The received echo has surface term S sub S and a depth term with amplitude S sub D, whose phase relative to the surface term varies with the dielectric constant. After making some simplifying changes to our math notation for the depth of scatterers and the dielectric constant, we can calculate the return from 2 such echoes, where the only difference between them is a changed dielectric constant of the medium, which results from changed soil moisture. We interfere these echoes to generate an interferogram. To model multi-looking, we take the expected value of the interferogram, assuming that we are using enough looks for a stable statistical average. This has an added benefit of simplifying the modeled interferogram, as many of the cross terms go to 0. To find the expected value of our modeled multi-looked interferogram, all we need is the radar cross-section and dielectric constant of the medium. We can extend this by calculating the closure phase across 3 interferograms where the dielectric constant changes in all acquisitions. While this equation for the triplet signal is very long, it is also quite simple. Again, it only depends on the radar cross-section and the dielectric constant in the medium. The closure phase is simply the phase of this triplet signal. We can explore the properties of the closure phase in this model by calculating a Taylor expansion of the exponential terms here. When we compute a Taylor series expansion of each of the exponentials in the model, we find that the linear portion, that is the first two terms of the expansion, produces an entirely real result, meaning that there is no closure phase produced. Thus, it is entirely the nonlinear elements of this model that have an imaginary component and can produce a non-zero closure phase. We see the result in this figure. For our soil moisture time sequence on the left, the first order linear approximation has zero closure phase at all points, seen in red on the right. While the second order approximation accurately matches the exponential version for small x. We can also see that the nonlinearity means that large derivatives or rapid changes in soil moisture have an outsized impact on the closure phase. The sharp increases in soil moisture here produce large spikes in closure phase, while the slower decays produce significantly smaller closure phases. The next step we take in our model is to calculate a cumulative sum of the closure phase. Why would we want to cumulatively sum closure phase? An analogy can be found in interferometric phase. Each interferogram shows velocity over a time interval, so we cumulatively sum the velocities to find displacement. Analogously, time-varying dielectric properties of Earth's surface produce a non-zero closure phase. Because the closure phase relates to the soil moisture change over a time interval, we cumulatively sum closure phase over time to derive a time series of soil moisture. On the left, we see the closure phase produced by our model for this time series of soil moisture, now for depth x at centimeter scale. You can see it has negative spikes, unlike the original soil moisture signal, and the peaks are not aligned in time with our peaks in soil moisture. On the right, we calculate a cumulative sum of the closure phase, and we notice a trend, as some of the previous presenters have also noticed. The nonlinear response of the model to changes in dielectric constant means that if we have a sequence of dielectric constant changes that are rapid in one direction and slower in the other, such as rainfall events and slow drying, the closure phase will respond much more strongly to the large change than to the sequence of smaller changes. Over time, this can produce an apparent systematic bias where the positive closure phases from rapid increases can dominate over the smaller negative closure phases from slower decreases, or vice versa. Closure phase is most responsive to large changes in dielectric constant across all three interferograms in the triplet. When we cumulatively sum the closure phase, this bias leads to a trend. Assuming a consistent asymmetry between the time spent wetting and drying, we fit and subtract a line to detrend the cumulative closure phase. So once we have this solid line on the right and subtract the dotted line fit, what we get is shown in red here. I'm calling this the detrended cumulative closure phase, and we can see in blue the soil moisture time series for comparison. We've averaged the soil moisture values over the 3 days included in the closure phase triplet. And it is evident from this figure that the detrended cumulative closure phase is anti-correlated to the soil moisture according to our model. Now let's see if we can use this relationship to estimate soil moisture. On the left, we scatter the detrended cumulative closure phase against the soil moisture. We find that they have a correlation coefficient of -0.87. We find a consistent trend line in black, and we use this trend line to generate an estimate for the soil moisture. The estimate is shown on the right and appears to track the soil moisture fairly closely. Now let's see how this can look in real data. To generate the closure phase, we use a Sentinel-1 InSAR swath in central Oklahoma, US, multi-look to a pixel size a bit smaller than a kilometer. We validate with 37 in situ soil moisture probes taking daily measurements at 5 centimeter depth. We look at data over 3 years from 2018 to 2021 using only adjacent scenes for triplets, so we have short temporal baselines. When we calculate the closure phase, the signals from the atmosphere and deformation are canceled out around the triplet, leaving only the closure phase signal. We create a time series of sequential closure phase triplets and calculate the cumulative sum over the time series. As in our model, we find that a cumulative sum of the closure phase results in a trend at nearly all sites, indicating that all sites likely have some unevenness in the rate of wetting versus drying. We once again fit a line to the trend and then remove the trend to find our detrended cumulative closure phase. I'll be demonstrating the process at one site in Seminole, Oklahoma. Without cumulatively summing and detrending the closure phase, it does not seem to correspond particularly to the soil moisture, as we can see on the left. But when we see our detrended cumulative closure phase derived from InSAR on the right and compare it to the soil moisture, we see a pretty clear anti-correlation between the two. This also seems to follow the model. So next, we'll try scattering detrended cumulative closure phase against soil moisture. The correlation between the two is negative 0.77 at this location, and we can again see a trend in these data points. We again use this correlation to create a fit line in black and then estimate the soil moisture values. So when we do that at this site, the prediction appears to track pretty closely between our measured and estimated soil moisture. It doesn't capture all the variation in soil moisture, but it does a decent job here. Now let's compare some other sites in our swath. Seminole is an example of a very clear linear relationship between detrended cumulative closure phase and soil moisture, but the Lahoma site has a weaker relationship, and the Hinton site exhibits practically no relationship at all. When we use these fit lines to estimate soil moisture, we see that while the estimate at Seminole tracks the soil moisture closely, Lahoma's does less well, capturing the soil moisture in some places, but overestimating periods of low soil moisture. At the Hinton site, the estimate fails to capture the variation in soil moisture at all. We might wonder whether there's any common way to estimate soil moisture at all sites. We plot the fit lines between the detrended cumulative closure phase and the soil moisture. Then we calculate the average of all the well-performing fit lines and use this fit line to estimate soil moisture from closure phase at all sites. We find that whether we use every site's individual best fit or the universal fit line, we find equally accurate results. This is promising as it suggests that from site to site, the detrended cumulative closure phase behaves similarly, so it may be possible to come up with a universal rule describing closure phase from soil moisture across locations, at least within a region. We might wonder about any relationship to terrain, and so we test that here. We find that the eastern side of our swath tends to have better estimates than the western side, and that pasture land tends to produce better estimates than grassland, which has better estimates for soil moisture than cropland. This may be because uneven irrigation patterns can complicate soil moisture signals in agricultural areas, and it likely also has a component related to vegetation growth or change in vegetation moisture, which results in greater moisture changes above the ground and therefore can have a stronger effect on the closure phase signal. So in conclusion, we've shown with our model that non-zero closure phase can result from interference of a surface and scatterers at depth. The surface and scatterers could include soil moisture, a vegetation canopy, snow cover, or other factors. I think many of the presenters in this session have discussed other possibilities, and Yugia, who is presenting in 2 presentations, has a paper that differently frames the mechanisms leading to this interference. Here we've shown that varying soil moisture with time leads to non-zero closure phase. an asymmetric soil moisture time series with different rates of increase and decrease can produce a bias that leads to a trend in the cumulative closure phase because of the nonlinear response of closure phase to dielectric changes. Detrended cumulative closure phase agrees with in situ soil moisture to a varying degree, and the level of agreement seems to be correlated with terrain type and vegetation density. This method could yield soil moisture at finer resolution than is possible using radiometric remote sensing, opening up new possibilities for high-resolution sensing of soil moisture. Lastly, I want to mention that we have a preprint out covering the material in this talk that you can find using the QR code or going to bit.ly/wigphase. Thank you for your time, and I'm happy to take any questions.
Thank you, Elizabeth. So we have time for a couple of questions. Anyone?
So do I understand correctly that the soil moisture you estimate is not for single dates, but is the average soil moisture for the 3 dates with which you calculate the closure phase?
Can you repeat the question?
Is the soil moisture that you estimate the soil moisture for single dates?
Oh, it's averaged. Yeah, it's averaged across the dates in the closure phase.
Across the 3 dates with which you calculate the closure phase?
Yeah, it's actually what I do here in the real data is I average across the whole time period included in the triplet, just because in situ soil moisture sensors have some variation. So I was hoping that by including more data and averaging over the whole time period in the closure phase, we'd get a bit more accuracy with the in situ data.
Okay. So you cannot separate single dates, but you always have 3 dates together.
Yeah, with this method, you couldn't separate single dates.
Thank you.
Thank you for the presentation. Very nice presentation it was. Just one question about soil moisture measurement you're talking about. Is it for the surface or at the depth?
So with Sentinel, we're likely not penetrating very deeply into the soil, especially when it's wet. So we are measuring roughly surface soil moisture. The in situ sensors that we're comparing to are at 5 centimeter depth, which was about as shallow as I could find for comparison.
And have you looked at the type of the soil that you have, or just you did comparison between in situ and InSAR measurements, just regardless of what type of the soil you have?
What soil type?
Yeah, you didn't consider, right?
No, we didn't incorporate soil type.
So you can you say that if you had runoff at some locations, it was just all based on whatever you had in soil?
Yeah, and I think that the soil moisture would have a comparatively large effect on the soil moisture dielectric constant compared to the soil type. And also, since we're measuring a change, soil moisture isn't typically soil type isn't typically changing at the same location. And what we're measuring is changes. What is changing is soil moisture.
Thank you.
I'm just wondering, your model, how dependent do you think it is on the vertical gradient of the soil moisture? So if you have a particular kind of average moisture within your penetrated volume, do you think it's a significant factor whether there's like a drying trend where it's there's a vertical gradient of the moisture versus a kind of basically a homogeneous difference between the dates?
Yeah, so are you saying from day to day?
Yeah, like if you had, if it was drying on one particular day, so you have a vertical gradient in the moisture, and then another day when it wasn't, so it was homogeneous, then your difference would have a vertical gradient in it. And I'm just wondering if your model considers that or if you think it would be a factor in the phase.
Yeah, our model doesn't explicitly consider that right now. We're kind of assuming the soil is a homogeneous volume. And again, because the C-band data doesn't penetrate very far, it's kind of a small volume. It's possible there's some dependence on the gradient in the soil moisture. Honestly, I would guess that that would have a smaller effect than whatever vegetation is over the top of the soil. Like, I think that our signal of the soil moisture is more likely to be inaccurate due to vegetation than due to not modeling the gradient of moisture in the soil correctly.
Thanks.
So thank you. That's a very good presentation. The real application, so when you deliver the soil moisture for the whole map, so for the bad soil is okay, it makes sense that it's soil moisture. But when it comes to vegetation targets like forest, so what exactly the phenomena you observe here? It's not exactly the soil moisture, or maybe it can be vegetation growing, something like that. Are your comments on that one?
Yeah, I think that absolutely over a place like the forest, and kind of as Yasser showed in his presentation, you're likely to be measuring vegetation moisture changes or vegetation growth changes. And so I am looking to apply this over the forest soon and see which signals are more dominant, whether it's a vegetation signal or a soil moisture signal. And it's also tricky because the vegetation and the soil are correlated, right? If you have more moist soil, you're likely to have more moisture in the vegetation, perhaps as it is able to grow more with more water availability. So definitely an interesting question.
Okay, so we move on to the next speaker, which is incidentally Din. And his talk is Efficient Earth Surface Monitoring with Tomasar from PSDS to ComSAR and the vital role of phase linking technique. Please.
Okay, good morning everyone. I am Den Ho Tong Minh from InSAR, so I am a research scientist over there. So we're waiting a little bit for, okay, slides coming out. It's coming out. It's coming. Okay, thank you. So in the previous tree talk, we're talking a lot about the closer phase, and then how we deal in, how we characterize in two perspectives. So the first is about how we can interpret the physics behind that closer phase, try to use that information, try to use that signal to exploit for some monster, for example. And another approach is we dealing with that problem based on statistical methods. So basically that when we go to a certain application like deformation, we don't want certain closer phase here. We want it should be close to zero, or in the perfect way it should be zero, even when we're dealing with multi-looking and so on. So in this talk, I discussed a little bit about that one. So a little bit fewer about the context. So as you know, that center one is very good, but it also is challenging because there is a lot of data available. So are we ready to dealing with that data in entire big data? So usually that's in the literature. There is a very good proposal about a Swenso estimator. So this is a very good performance, very good algorithm, and very good scheme in terms of the distributed scatterer. So what about when we're dealing with other stable target like persistent scatterer? So our objective is we just a little bit discussion about how phase linking working, because you heard a lot in the previous tree talk that with the phase linking, there is usually that's the way to verification, a way to validation, or something with the other processing in time of SPAT, for example. And then I will introduce about algorithm, what we call the COMSA. So basically that's algorithm to combine the BS and the DS together in the framework of the phase linking. And then I a little bit introduce for the Tomosa. That is my one to implement that algorithm, and I made it open source recently. So in the last 20 years, so we have a lot of algorithms to dealing with the star data. So what exactly why we have many algorithms? Because with star data, we have a lot of decorrelation because as a function of time, every change in varies temporal decorrelation. So the main formula for that problem is we need a long time series data, and based on that time series data, we are able to find a certain position with the good coherent, something like persistent scatter or a good distributed scatterer. So we have some methods, something like, okay, so PS or S-path, or if we combine together, we can gain more information, and maybe it's the best performance with BS and DS methods combined together. And in the frameworks of the DS, we are very good solution for the bit InSAR data. And recently I proposed to combine with BS, or what we call COMSA. So just a little bit for visualization, what exactly it is. So so I refer to the image on the top on your left. So basically with the BS, we just need one reference image. You will have a certain network like this one, like a star, like bitmap bump, and you see that's the figure. So why we just need one reference in that BS? Because BS just one point. So if we just take one reference, it is single loop. It is single loop. So if you take the closure phase is on way 0, so there is not necessary to combine a certain network in just a BS point. So when we go to the DS, it should have to do some kind to dealing with the decorrelation. So with the distributed scatter, they're dealing with decorrelation based on a certain kind of minimize the decorrelation in terms of time, in terms of geometry. So that's why they will have a certain network like this one. And recently not really recently, that's about 15 years ago, so people try to come up why we had to develop a certain network and try to find which is the network with the best. So why not use everything together and put everything together? And when we put everything together here, and that the key problem is it's a lot of work have to do, a lot of equation have to show, and a lot of equation, a lot of metric to have to do inversion, and it's complicated. And people figured out, okay, we have to find a way to do it. It's make more simple. So and then the way people do it, they try to inverse the below the BS full network to go back to this BS a single reference network. So basically, what the DS network is, they want to do it. They want to transfer that all possible combination to a just equivalent single reference problem. So and that's the problem is a fail linking. So basically, that's just the product we have the end images available. So if we combine everything together, we have something like n times with n-1 divided by 2. So in case of the BS network, so it's just about n-1 value is sufficient because we have a 0 closure phase. So fail linking is a statistical matter. So remember, so in the previous talk, when we're talking about the closure phase, it's always referred to the other aspect of the problem. That is, we want to retrieve a signal inside the closure phase. So we want to do something like physics interpretation for that problem. But in here, we prefer the problem based on statistic methods. So we want to avoid that closure phase non-zero. So basically, the problem is we combine everything together and transform it into a single equivalent, a single preference time series data. So the problem is quite straightforward nowadays because you can see here. The way we combine everything together is we just put it in a certain covariant matrix, like coherent matrix. Here you see that is two-dimensional matrix, and then if you concerned in a certain position in column M and the row M, you will see the problem with just the minimal problem like this one. So you have something like a certain kind of wave factor, and then we time with the cosine of the phi n m, and the other parameter is the theta n, and the theta m. That's the parameter we want to estimate from their optimization. So all the proposal during the last 15 years for the Felinkin, it's just different. It's just different about the wave factor here. So the gamma frame here. So here it's a little bit main characteristics of the main Felinkin algorithm. There's a lot, but here we can classify into approach. Basically, it's based on the computation for the problem, and the other one is based on the coherent matrix to improve the data before we do the inversion. So based on the first one, since the works of the Guarnieri and Tebadini, they propose to use that's one the frameworks of tomography SAR. So basically, that even in tomography SAR, with just a few images, they can exploit the best information to improve a lot in terms of the phase calibration in the tomography work. So the idea of Felinkin is from that literature. And then after that, there is exploit for that concept to do for example, with the phase triangle in the squeezer, and the other one with eigenvalue decomposition, and so on. So so you see it, every algorithm is different about how we are using the wave factor during the optimization. And here it's a little bit of performance. So the performance is ordered from low performance to high performance to facilitate the visualization. So basically the coherent and the EVD, the eigenvalue decomposition, is almost similar performance. And then we go to ME and go to maximum likelihood and go to regulation and go to compression. While the compression is very close to the lower bound, because that's during the compression process, we are able to cancel out all the noise in the compression version. So, and then recently I just think about the roots of concept, how we can use the recent AI technology like deep learning to learn something, because you see with the Felinkin, the algorithm is there, and then a lot of proposal, and not necessarily which one is the best one. So if we are able to put everything together in kind of framework and like for deep learning, we can gain something for the next generation. Here is just the first concept where there's not much to say, but this one is just a very simple synthesis data set to performance to see, okay, and then we see the quite positive that you see in the E and the F, the last slide. So you see with the E and the F, we are able to reconstruct the data with respect to RD1. So the input, you see the input is the big one. So the input is the real data, something that's one. It's always noisy like this one, but when we do Felinkin, we are able to retrieve the signal for our problem. Okay, so that is the problem of Felinkin. So, and then we move from the BS to the combine with the DS. So the key problem when we combine is we have to able to be sure that the quality of the distributed scatter we put together with the BS, it should be quite, say, similar quality. It means we have to find a way to enhance, to emulate the DS to quasi-BS. So the way to do that one is we have to be careful that when we do the Felinkin, there's a certain kind of assumption that it means that not all the bit cell can be the same distribution. So we have to be sure that we dealing with a certain kind of Gaussian distribution target. So to do that one, we have to be sure that we have to find a certain bit cell which share similar statistic behavior, something like statistical homogeneous bit cell, by applying a certain test like t-test or like Anderson test. And then based on that family, we can form the main actor. So basically that's the covariant matrix like this one. And then we dealing with the Felinkin to find the best optimal n-1 phase value. And then if there is a certain fit with the model, we can replace that value with the original one data. So whenever we're done with the BS processing, we improve the quality of the DS. We put together with the BS and the processing of the BS, DS is almost the same classic traditional BS methods. So the BS, the DS is powerful, but the problem is we have to do the full covariant matrix. Like the first line you see here, you have to do the full covariant matrix here. Like in this example, it's just about 90 90 by 90 matrix, it's easy to do eigenvalue decomposition. But you know now syndrome 1 is something like 400 images and 400 image, 400 by 400 matrix. It's not really easy for computer to do the inversion. And maybe in future we have maybe 1,000. So it's not really efficient to do inversion with that kind of matrix. And then what the problem is, if we have a new future acquisition available, what we have to do, we have to recalculate everything. So the idea is, instead of to dealing with the full network like this one, we divide by a certain mini stack. For example, I divide in the second line, I divide by 10 by 10, so we have a mini stack, 10 image, 10 image, 10 image, 10 image. So instead of dealing with the covariant matrix of about 90 by 90, we're just dealing with 10 by 10 image, a 10 by 10 covariant matrix here, and it must be straightforward to do inversion. And then during this mini stack here, we do fail linking inside 10. So we will do the fail linking. We will do fail linking for this one. So basically, there is a mini stack about 10 images. So we do the fail linking. So we got the 10 weight factor, and then we do a certain coherence summation in that original 10 images. So we put it together. We take assumption, and we take a summation focusing, and we got the compression version like this one. So basically, we are able to exploit the fail linking to deliver a certain way to sum the original single look complex data from 10 image to 1 image like this one. So we repeat the procedure for all the mini stack, and we got about 9 compressed single look complex version here. So, and then we are able to do fail linking again to join link everything together. So we have the compressed version. So whenever we have a new acquisition data, so instead of dealing with 90 by 90 image, we have to here just 9 images, and the new future acquisition available. So the problem is really a lot. So we don't need to recalculate everything. So whenever we need, we are able to use in that compressed version to link with the full time series data. Okay. And then we implement this one in the Thomas software. So this is open source. So if you want, you can go to my GitHub and you see this one. And the concept is very friendly in terms of the big data processing. For example, with true image and with the size like this one, it requires a lot in terms of the DS processing, but just about 45 gigabytes for the concept. So it's very friendly in kind of the big data processing. And then a little bit of demonstration for how it's going on. So you see, using with the complex algorithm, we get a lot in terms of the denser point target for analysis. So basically, through image, we see the phenomena in almost the same, but on your right side, you see a lot of information available. And then we move to a little bit more focus to a certain small area here. So on your top, on the left, so I do exactly the same images, but so in the small area here, so the previous one is very big one, so 250 kilometers by 350 kilometers. Here's the small one, and we put together the small and the big one, and we see the correlation is almost similar. The error is something like about less than 1 millimeter per year. So we a little bit focus on about the small error here with 3 different data sets. So with syndrome 1 ascending and descending, and also with Cosmos gamma data. We see the same spatial distribution. Of course, if we go into a little bit detail like something like with the profile from A to B, we see a little bit different, but it's very tiny. So, and then we have some validation because there is data here. So not much to say, but the conclusion to summarize is the fail linkings, I repeat it here, this is the way to handle in statistical way. So it's not the physics, we don't want to retrieve any physics information signal here. So if you want to do retrieve some information, something like some monster, you have to avoid this technique. And then in future research, I think the deep learning can be a valuable tool to improve data performance. And then Tomosai is my first domain public tools available to my knowledge. I don't know the other one. And then there is also some research and some forum to discuss on everything. So I'm free over there, always available over there for you. So this work is supported by just a very tiny project. So I'm open to join with you in a certain kind of project to do future work interesting for community. Okay, I'm done. Thank you a lot for your attention.
Thank you very much. We do have time for a couple of questions.
Okay, I'm available, everyone. Okay.
Thanks for your good presentation. So I have two questions. First one is why you name your toolkit TomSAR, because TomSAR in our community we may refer it to something like tomographic SAR, and for work in urban scenarios and for separate different scatters within 1 pixel. So this is my first question. And the second one is I have seen one of your slides that you have a comparison between PS plus DS and your compressive SAR maybe. I find more points can be found in your method. So I was wondering, because you didn't use the full stack in the diagrams, and so how it can be guaranteed that more points can be kept if less in the diagrams was used. Would you explain a little bit on this? Thank you.
Okay, thank you for your question. So maybe I try to rephrase your question for everyone to follow, but maybe if it's not correct, please correct me. So the first question is about the TomSAR name. So why is the name of TomSAR? Because I did my best in TomSAR. So from that one, I have a lot of course for SAR tomography, for InSAR, for interferometry, for polarimetry. And TomSAR is not immortal, it's just an advanced technique for interferometry. So I have kind of say from end-to-end processing for TomSAR. But when I give the public domain tools, so I just focus on the backend with dealing with the PS and the DS processing. That's why I keep the same name, TomSAR, but people confusing about the TomSAR techniques and the TomSAR for the BS and DS. That's the first question, is correct. And the second one is when people combine the BS and DS, people do it separately. People try to enhance the quality of the DS, and then they put the BS separately, and then wherever they are able to improve the DS to become the quasi BS, and they put it together. So the same thing we do with compression. We do compression with just the DS, and then we combine with the BS. So we don't do anything with compression with the BS. We don't touch that one. Is it correct for your second question? Okay. Okay, thank you. Yeah. Okay.
Okay. So thank you. I think we should proceed to the next. Thanks a lot. So we proceed to the next presentation. This will be given by Yuyue Zheng from the California Institute of Technology. The title is Modeling Soil Moisture with Cumulated Closure Phase of Interferometric SAR Measurements. Please.
Good morning. My name is Yujie Zheng. I'm now at University of Texas at Dallas. So this work is started when I was a postdoc at Caltech, working with Hirash Fatahi. So my topic today is about the intricacies of modeling soil moisture with closure phase bias. Many talks before me have already discussed what is non-zero closure phase, what is short temporal bias in time series. So I don't have to do that anymore. I just like to highlight the connection between these two phenomena. So they both share the same governing process, a process that induces complex changes, not just phase shifts in interferometric measurements. And because of this connection, we can actually use one to correct for the other. So last year, we have a study published about using sequential closure phase to do bias correction. And the study area was the California Mojave Desert, and we find a lot of bias in the area surrounding the dry salt lakes. So I'm not going to get into details here because it's not the focus of today's talk, but what I really want to show you and what really gets me here today is we really want to understand closure phase bias, not as noise, but as a signal. Take a point adjacent to the Bristol Dry Lake as an example. So this is the closure phase bias we extracted for this point. So you can see that there is, we observe this cumulative uplift signal that's about 4 centimeters in 4 years. And it's not linear, it's rather episodic uplift episodes. What's interesting is when we compare the precipitation records in this area, you can see that the uplift episodes align very well with the precipitation events. And if we superimpose the cumulative precipitation events, this relationship is even more evident. And we know that InSAR correlation can be infected by rain events in these type of hyper-arid regions. For example, from this plot presented by Jordan et al. 2020, you can see that whenever it rains, we have a transient loss of correlation, and then there is this gradual recovery of correlation as the soil dries. So we're thinking, could we be seeing the same thing here? The soil drying process to be specific, but not just in correlation, but in phase. And to really understand that, this is a nice correlation plot, but it's not causal. So we really need to dive into the physical models. And very luckily for us, we don't have to do that ourselves because the InSAR community has already produced a few interferometric models for soil moisture. For example, the Dizan et al. 2014 has described very nicely how soil moisture change impact the interferometric phase. What we do here is that we build upon this analytical model and we discretize it. And the advantage of doing that is with a discretized model, it's very easy to implement for numerical simulation. And secondly, it's easier to adapt to more complicated scenarios where you might not be easy to get a solution analytically. And thirdly, the reason I like it so much is that we can actually start from single look radar returns and work our way through interferometry, multi-look, time series analysis, so we can really understand the whole process. So here is our general approach of trying to understand closure phase bias as a signal. We'll simulate a series of single look complex images that go through different soil moisture time series. And we'll specifically experiment with 2 types of environment. The first would be an arid environment where we would see, so it's like a desert environment. Usually the soil moisture is at a low level, and except when it rains, you have a sudden increase in soil moisture and then a gradual decay. And the second case is a wet environment, which more like agricultural fields or croplands, where you have a soil, where the soil moisture is usually maintained at a high level, except when the weather gets dry and you have less rain, and then the soil starts to dry out. And then the farmers will need to irrigate more to recover the soil moisture to its preferred level. Okay, so let's look at the first case, an arid environment. And here I'm showing you on the left is an example of in situ soil moisture measurements at a desert, in the Mojave Desert in 1 year. So you can see, as we described earlier, soil moisture was generally low except when there's these isolated rain events. Now imagine a time period in one of these deserts where there are 3 distinct rain events. So the y-axis here is soil moisture, and then these bumps are post-rain soil moisture variations. And for simulation purposes, we made both the magnitude and the duration of these post-rain soil moisture variation to be different. What we do now is that we simulate 100 SAR acquisitions that go through these rain events And then we form interferograms, and we multi-look them, and then we do time series analysis of different bandwidths. And these are the resulting time series. And when I say bandwidths, for example, bandwidth 1 analysis, it means that it uses a network that only has connection 1 interferograms, and bandwidth 5 is only have connection 1 through connection 5, and full network is using all possible pairs. So you can see this diverging time series, which is what we see in real data as well. And I would just like to quickly point out that we can learn a lot from these simulations about the origin of bias, why it's cumulative, why it's fading, etc. But okay, so I'm not gonna get into details here because the time limit. Rather, I'll just show you what the closure phase bias look like. So that's the difference between the bandwidth 1 time series and the full network analysis. As you can see here, the simulated closure phase bias closely mimics what we see in real world data. And first of all, it's cumulative. And as you can see, it also confirms that the uplift we see in these biases corresponds to the drying in the soil. And secondly, the amount of uplift is really a function of how much the soil moisture varies and how long it varies. So it's it depends on both the soil moisture decay rate and variation. And slower decay and greater variation result in larger uplift. And yeah, so to sum up till now, we have this forward model that we can start from soil moisture values, and we will end up with a predicted bias time series. And now we can validate that with real-world data. So continuing with our California Mojave Desert example now is a full frame, so we can include an in situ station, which is the fourth station marked by the cross in the map there. And on the right is the in situ soil moisture measurements for this station. Taking the soil moisture measurements at SAR acquisition dates, we can feed them into the forward model and generate a predicted bias. And we can compare that with the observed bias, which actually matches really well. So now we can have some good confidence that our forward model in this error environment case works pretty well. And now we can start to think about how to work the other way around from closure phase bias to soil moisture. And thanks to this incredibly simple form of bias, and when we have a bias that looks like this, we almost can have a good guess of what the soil moisture looks like. We know the uplift in bias corresponds to the soil drying. So we can make a guess of the soil moisture that looks something like this. And then we can feed our guess of the soil moisture into the forward model and generate a predicted bias. And we may get something like this. That just means that we have overestimated the soil moisture variation, so we can go back and modify our guess and then generate another prediction. So by doing this search, we'll eventually arrive at a solution that fits the bias, fits the data. So to sum this up, basically we're proposing a 3-step inversion scheme. The first step is to identify a disturbance window or disturbance windows. And this is where soil moisture values derail from their base values due to either a rain event or something else. And the second step is we try to describe the soil moisture time series with a base value and an exponential decay model that describes its evolution in the disturbance window. And the third step would be to search for the parameters that gives us the best fit to the bias time series. So now let's see how this works with real data. Coming back to the real data example from the Mojave Desert, this is the bias that I have just shown a few slides ago. The first step is to identify the disturbance windows. So it will look like we have two, but actually I find it's much easier and more accurate to actually identify these disturbance windows from the phase gradient instead. So in the phase gradient, each of these peaks or upward triangles corresponds to one disturbance event. And with some threshold on the baseline variations, we identify 6 disturbance events for this case. And with that, we can start to populate the soil moisture time series and start to search for the best parameters. And this is after some quick search. This is the result. On the top panel is the derived soil moisture in orange or yellowish color. And on the bottom is the fit of the observed bias versus the predicted bias. And on the top, it's also I also plotted the in situ soil moisture measurements, so you can see the comparison between the two. Overall, it's a pretty good agreement. Oh, yeah, and interesting, I find that bias gradient itself may be able to serve as a proxy for soil moisture. This is because previously we have used bias gradient to identify the disturbance windows. So, and also usually the bigger the disturbance, the bigger the gradient. So that's why you see this nice correlation. I do have to point out that you can see that the bias gradient is more symmetric when the soil goes increases, rises, and falls. But so that doesn't capture the really asymmetric nature of soil moisture wetting, soil wetting and drying process. But nonetheless, this could be an effective proxy, which I think a lot of the presenters have shown earlier before as well. Yeah, so now let's go to the second scenario, which is a wet environment, or agricultural field-like environment. This is on the left, again, is an example of how in situ soil moisture measurements vary in an agricultural fields in 1 year. As you can see, it's mostly maintained at a relatively high level, and when it's summer, it gets dry, and then there's increased irrigation and an attempt to bring the soil moisture back to its desired level. And similarly, like before, we simulate for 3 different disturbance events. Each of these events will have different magnitudes and duration. And repeating the steps for simulation, we can generate a predictive closure phase bias. And you can see now it's opposite. It's basically a mirrored image of what we see for the arid environment case. You have this cumulative subsidence in bias. And the subsidence episodes corresponds to soil moisture increase, and the magnitude also depends on the amount of increase and how fast it increases. And slower increase and greater variation will result in larger subsidence, apparent subsidence. Yeah, so now let's look at some real data. And this is a data set in the Central Valley, California, consists of only connection 1 and connection 2 interferograms. So they have a temporal baseline of 6 or 12 days. And yeah, so they can, so I have checked all the interferograms. They retain very good correlation over the agricultural fields. So the map here is a closure phase bias velocity map. You can see that the color is mostly blue, which means it's the bias is negative. That means it looks like a subsidence. And the outline of the bias aligns very well with the agricultural fields. The bias is actually quite big. As you can see from the scale there, it's from -3 centimeters to 3 centimeters per year. And on the right is an example of the closure phase bias we see from a point that's marked by the yellow cross there in the Sacramento Valley. So you can see this is the familiar shape of cumulative subsidence, episodic subsidence. And now if we compare the precipitation records in this region, you can see that the subsidence actually happens when there's, in the summer, and when there's not much rain. So that also confirms our simulation model earlier. So we can do the same thing again for the inversion. So on the top panel is the predicted and observed bias, and on the bottom is the orange dots are the derived soil moisture from the bias, and the gray dots are SMAP soil moisture. So unfortunately, I was not able to find any in situ soil moisture measurements here. So, but it's tricky to compare these two because we know that SMAP soil moisture is of much larger spatial scale. It's really an average over kilometers of space, whereas the bias pixels is about 100 meters in size. But nonetheless, I want to point out that you can see there is this wetting period in summer in both derived data sets. And yeah, so in summary, we have produced a discrete soil moisture model that can link soil moisture variation to closure phase bias. And the advantage of this model is that we can really make it as complicated as we want to adapt to realistic scenarios. Right now, we are using the simplest form. And we have also shown some observations of closure phase bias in two different environmental settings. One is in desert regions where you see the bias as uplift, and one in the agricultural regions where you see the bias as subsidence. And we have shown some forward model that can link soil moisture variations to bias accumulation very nicely, and I have shown some initial results for the inversion. And there are some potentials of using closure phase bias for modeling soil moisture, and one is because you can see that the way we link soil moisture variation to bias accumulation is very straightforward. You can very easily visualize it. This is comparing to trying to work out the inversion directly, either with closure phase or with the SAR amplitudes. And of course, it offers potentials to detect drought onset, produces high-resolution soil moisture maps, and scale, and it really scales with global time series products. Of course, it has its limitations. For one, it has limited temporal resolution, which is in turn limited by SAR acquisition intervals. And also, our inversion scheme is at its very early stages, and it has yet to be tested with more extensive data. I think that's all I have. Thank you.
Thank you for this very interesting presentation. So, yeah, please go ahead.
Yeah, nice talk. I have a question for you, but also for the other speakers. My takeaway message from all of this is that if you want to detect soil moisture, use sequential interferograms. But if you wanted to avoid soil moisture, you would use longer time span interferograms, and that time span would be dictated by the decay time of that property. But what bothers me a little bit is, I think at Yasser's talk, he showed annual cycles, which suggests maybe that time span is annual.
Yeah, so I really think the simulation can, okay, sorry, I'm trying to go back there. The simulation can really help us understand about the time span you need to have to avoid the bias, because you can see here, the reason you have this cumulative bias in short temporal baseline is because, first of all, you have this asymmetric response from soil wetting and drying. So that produces a signal. And when you use short temporal baseline only, you have a short memory. So you can't really distinguish what is a real deformation and what is not. And so that's why you see the bandwidth 1 analysis, it starts to build up. But once you have pairs that actually span this rain events, so it knows that like before, what is like before the rain and what is like after the rain. Like, for example, if you see for the first rain events for a bandwidth 5 analysis, it doesn't really show much bias. So basically, it's not how long that you need a threshold for the temporal baseline. It's more about the what's happening there. Like in this example, if it's a desert area, and you probably just need pairs that have longer durations than the rain, than how long, than the post soil moisture disturbance time. And for agricultural fields, it might be more complicated. So it really depends on that.
But this bandwidth 5 included
1, 2, 3, 4, 5.
What
Yes.
if you avoided the short ones and just kept the 5?
That's fine. Yeah, sure.
It would be better.
So another great thing about the simulation is you can easily try that with the simulation and see how well it works. Yeah.
Yeah, there is one more. I think we take one more and then we defer the rest to the roundtable, which will be tomorrow after the second session in this topic. So anyone who wants to discuss this further after this question, please come to the roundtable tomorrow. There is one question over here.
Thank you so much for the nice presentation. Now that you have the simulation tool, I was curious, in a weird world where there's a rain, but it never dries, so there's a step function, and what would be the response of what would be the result of your simulation?
So are you saying that if it's like a step function and then never dries? Yeah,
Right.
so I think it will look something like the food network. But I don't know. So that's, again, it's a thing that we can try out with the simulation.
It's interesting that it seems to be more sensitive to the gradual drying phase.
Yes,
than the
yes,
step
yes, it
itself.
is. So we find that it's not only it's sensitive to the speed of drying and also the amount of drying.
So you can try a step function and see what happens.
Yes,
Thank you.
we can do that.
Yeah, I think not to steal the coffee break from everybody, I think we have to close now and return for the roundtable tomorrow.